This is the first lecture of topic 30.1 arenes of topic 30 hydrocarbons. Now, what are arenes? Arenes are compounds that contain a benzene ring or multiple benzene rings. The simplest arene is benzene itself. Now, what is benzene? The first reasonable structure of benzene was suggested by Kekule in 1865, and it looks something like this. Now it satisfies the formula C6H6 of benzene, and here we can see it has 3 single bonds and 3 double bonds, and it was considered correct at that time. But as science and technology advanced and we became able to measure the bond length between molecules, this is what we found out. Now these results seemed quite absurd from Kekule's perspective. Shouldn't there be 3 bond lengths of this size and 3 bond lengths of this size? But the carbon carbon bond in benzene are all of the same length and seem to be of this size. And this value is somewhere between these two values, which suggests that the carbon carbon bond in benzene neither has a single bond character nor a double bond character. And this here is the correct structure. This one. We can see that one carbon here forms a bond with this carbon and forms another single bond with this carbon, and it also forms a bond with hydrogen, which is not shown in the skeletal formula. And now there's an electron left. There's an electron left at every carbon. Now these 6 electrons take part in forming the delocalized ring of electrons, which is very stable. Okay. Another proof that Kekule's structure is wrong is that if there were carbon-carbon double bonds in benzene, it would undergo addition reactions like alkenes. For example, ethene will decolorize bromine water, but benzene will require much harsher conditions to do so. Now that we know the correct structure of benzene, how would we describe what we know? In CIs, the examiner often asks you to describe the structure of benzene. We know that it's hexagonal and it's planar as well, but what does planar mean, right? Imagine a paper, a smooth paper, okay? It exists in only one plane, which is depicted by this gray shading. Now, if you take this point and you pull the paper from this point, it will look something like this. And you can see that it now exists in two separate planes, which are depicted by the red and yellow shading. These are two different planes. Now this piece of paper no longer exists in one plane. It is not planar anymore. So it exists in two plane. Similarly, benzene is a structure that if you join all the carbon atoms by imaginary lines, they would all be on the same plane. Why is benzene planar? Benzene is planar because it
Each
forms
carbon in
three
benzene
bonds. Forms 3 bonds, 3 sigma bonds. Now, why does it form 3 sigma bonds? Because this is its ground state, 1s2, 2s2, 2p2. This here is its excited state, into which it goes before forming bonds, 1s2, 2s1, 2p3. This electron over here moves to this orbital. Now, this p orbital, okay, this p orbital takes part in the delocalization thingy. We're not talking about it right now. But this s orbital and these two p orbitals, this s orbital, the shape is shown over here, and the shape of these two p orbital is shown. These three hybridize together to form three sp2 hybrid orbitals. These three hybridize to form these three sp2 hybrid orbitals. Now, carbon uses these three sp2 hybrid orbitals to form a bond with a carbon, with another carbon, and with hydrogen. Now, what happens to this p orbital? This p orbital takes part in delocalization, like this. Now you can see that, right? The upper lobes are forming this pink ring, and the lower lobes are forming these purple ring. These are not pink or purple. I'm just showing you in this way that this is how they bond together. The p orbitals bond together in a parallel fashion. Now these are not sigma bonds. Sigma bonds is direct overlapping of orbitals. It's a kind of a pi bond, and these pink and purple thingy also merge together, kind of mix together. So hence we form our delocalized ring of electrons that is shown by a circle in benzene. Okay, now that we understand the structure of benzene, let's try naming some aromatic compounds. Okay, now this here is chlorobenzene. We don't need to call it 1-chlorobenzene because there's only one chlorine atom. This here is nitrobenzene. This here is phenol. Okay, you can call it hydroxybenzene, but that is not really used. So a more common name is phenol, so call it phenol. And this here is phenylamine, or you can call it aminobenzene. And on this one here, okay, we'll number this as 1. This is a phenol, but it has bromine groups attached. So we'll call this 2,4,6 tribromo phenol. Okay, now the reactions of benzene. The delocalized ring of benzene is very stable, and benzene likes to maintain this stability. This ring has a high electron density, so it attracts electrophiles. Now, we have an electrophile and we have our benzene ring, and they're both attracted to one another, but benzene also wants to maintain its stability. Now, what happens? Benzene undergoes electrophilic substitution. In this way, it does not lose its stable ring. Now, let's study the mechanism of electrophilic substitution. What happens is that this ring of electrons is attracted to this electrophile, okay, and we show this by drawing a curly arrow from this circle to this electrophile, right? Now what happens is that two electrons from this delocalized ring of electrons move to form a bond with this electrophile, and a positive charge develops over here since two electrons just moved from here. Now the electrons in the carbon hydrogen bond are attracted to this positive charge, and they neutralize this positive charge, and the ring is formed again, and hydrogen is broken from the benzene ring, and we form a cation of H positive. Okay, now we're done with today's lecture, but here is the content of the next lecture, and these are all the reactions of benzene you need to know for your A level chemistry, right? Electrophilic substitution, you need to know halogenation, nitration, Fiedel-Crafts acylation, Fiedel-Crafts alkylation, you need to know about oxidation of side chains, reduction of side chains, and hydrogenation. That's all.